we chemists care a lot about how much solute you've got dissolved in a certain amount of solvent or solution. So we care a lot about the concentration of solutions. We're all the time talking about and thinking about how concentrated the solution is, how much I've got of that chemical in that particular solution. And we have different ways of expressing concentration, which is how much solute you've got dissolved in a particular quantity of solvent, or in most cases, a particular quantity of solution. And you can look at mass percent, and it has that has the percentage symbol and the letters mm, which means mass. And it means mass of solute in grams divided by the mass of the solution, not the solvent, the solution as a whole. Again, in grams and times 100 because it's a percentage. Or you might have a mass volume percent, and that's how many grams of solid you've got in milliliters of the solution. And again, times 100 because it's a percentage. Or you can have volume percent, and this is very common, for example, for alcoholic drinks. If you look at the percentage, the strength of alcoholic drinks is percentage VV, and means volume. So that's very common when you have a solute, which is a solvent. It's a liquid, but the solute is also a liquid. In this case, alcohol in water, and this is milliliters of solute divided by the milliliters of the solution, and again times 100. Molarity is a particularly popular one for chemists, and we spend a lot of time talking about molarity, the molarity of hydrochloric acid, the molarity of sodium carbonate, the molarity of sulfuric acid, sodium hydroxide. And that is how many moles you've got in the solute divided by the volume of the solution, and the volume of the solution in liters or cubic decimeters if you prefer to use the SI units. And finally, molality, which is not, it's a bit confusing because you have a small m, which can look at it as if it's mass, but it's not. It's actually molality, which is moles of solute divided by the mass of solvent in kilograms. And that is not something it's more typically used in engineering, chemical engineering, when you're looking about a factory, because it's actually sometimes much easier to weigh a solvent, how many kilograms, rather than worry about the volumes of solution. So we are not going to typically use molality. We'll be mostly using the other four, and specifically possibly molarity quite a lot. So mass percent, units of mass percent, for example, milk, to tell you if you have skim or semi-skim or whole milk, that those percentages are in mass percentage. Mass volume, a typical example is physiological saline solution that is given in mass volume. As I mentioned, volume, things like rubbing alcohol, in general, any alcoholic drink or any alcoholic solution will be given in volume. And molarity, again, is very common in chemistry, and you have used molarity before, the molarity of hydrochloric acid, the molarity of sodium carbonate, etc. And you will use it more in the future. And to use molarity, and to do calculations using molarity, you will need the formula, which is molarity is moles of the compound divided by the volume of the solution in liters. But you will also probably need at some point to use moles, molecular mass, and mass in grams, because you will need to weigh this amount of hydrochloric acid to create that solution, which is 1 molar, for which you will need to convert your moles into grams. But the definition is this one: number of moles of the solute divided by the volume of the solution, and specifically in liters or cubic decimeters if you prefer to use SI units. So just a couple of slides to reinforce a little bit the concept of molarity, because it's normally the one that students tend to struggle a bit more, because it's very common for us chemists to use it, but it's not something they use in everyday life. So molarity, what's a solution, a molar solution, or moles per liter? Well, if you have, let's say, a substance that is 6 molar or 6 moles per liter, what does it mean? Well, it means that you have 6 moles of the substance you are dissolving in 1 liter of solution. And that's what it gives you, your 6 molar solution. So just to reinforce, molarity, as well as any other concentration units, is not how much substance you've got, but how much substance you've got with respect to how much solution you have in total. So for example, if you have the same 6 moles of substance, but this time you dissolve it in 0.25 liters into 150 milliliters, and you're going to calculate the molarity of that, the 6 moles are the same, but the volume you are using is not longer 1 liter, it's 0.25 liters. And that gives you a 25 molar solution, much more concentrated than your 6 molar solution of the previous example. And that is because, yes, you still have 6 moles of substance, but you have used a much smaller volume. So when you actually give the concentration in moles per liter, you end up with a much larger quantity. At 24 moles, there are 24 moles of that substance in a whole liter of that solution. Very briefly, another couple of concentration units that you may or may not be familiar with. They're particularly useful if you're working with environmental samples, if you're working with, for example, contaminants. That's the type of units that we will use in an environmental context, or when we're following a particular pollutant, or we're looking at the concentration, accumulation of a particular pollutant in an animal or a plant or a water sample. And it's parts per million and parts per billion. And these are units that are defined not as what they are, but the relationship between both units. So what does part per million means? Well, if you have 1 part per million of something, it means that you have 1 unit of that something in 1 million units of the total solution. So the million means that the difference between the unit at the top and the one at the bottom is a million. And parts per billion is 1 unit of whatever you are measuring in 1,000 million units as the solution. So if you imagine you have a solution and you imaginarily divide that solution in 1,000 million identical units, each of those units, each of those little cubes would be 1 ppb, 1 part per billion. And it is 1 American million. It's 1,000 millions rather than a million of millions. So again, that's all well and good, parts per million, 1 unit in a million units, or 1 ppb, 1 unit in 1,000 million units. But when you're going to measure something, like when you're going to weigh something and then dissolve it in a certain amount of water, there's no balance that will measure units, and there's no volumetric flux that will measure units. So you can translate those into units that you can actually weigh or measure. It's typical for analytical chemistry, so anything that has to do with analysis of food or environmental samples or contaminants or accumulation of pollutants, pesticides, metal ions, whatever you can think of in humans, in plants, in animals, in the soil, in the water, in the air. It's very typical to work with ppbs, ppms and ppbs, because in many cases, if let's say chromium-6, there are certain chemicals that are particularly dangerous, that the very, very tiny small amount is enough to cause harm. So you do want these sort of very small units that can measure 1 unit of that particular chemical in a million units of solution is already a problem. So what you do is you have something that the unit at the top and at the bottom are a million units apart, or 1,000 million units. So for example, what's 1 ppm? Well, it could be 1 milligram per kilogram, because between milligram and kilogram there are 6 orders of magnitudes. Or if you were studying, for example, ppbs, what would be a ppb? Well, that would be 1,000 10 to the 9 orders of magnitude separate between the top and the bottom. So you could have micrograms per kilogram, because nanograms per kilogram, because there are 9 orders of magnitude in between those two orders. So milligrams per kilogram are a typical example of ppms, and micrograms per kilogram are a typical example of ppbs. But it doesn't have to be those. Any two units of mass that are 6 orders of magnitude apart or 9 orders of magnitude apart would also be considered a ppb or a ppm or a ppb respectively. If you're working with water solutions, then you can assume that 1 kilogram of water is 1 liter of water. So again, we use the 1 unit over a million units, and as we decide before, well, it could be 1 milligram of, let's imagine, a contaminant, cadmium-6, or you know, a pollutant or a chemical you are tracing in your sample in 1 kilogram of water. Because this is so small, you kind of take that the solution and the water weigh the same, so 1 kilogram. And 1 kilogram of water, because of the density of water, is 1 liter of water. So actually, milligrams per liter are ppms. So you can talk about 1 ppm of a substance, or you can talk about 1 milligram per liter of the substance. And if you're looking at ppbs, again, we discussed in a previous slide that is 1 microgram per kilogram. In this case, per kilogram of water, you're talking about a water solution, and 1 kilogram of water is 1 liter of water, and that would be 1 nanogram per liter. So milligrams per liter would be ppms in water solution. 1 ppm of cadmium in dissolving water would be 1 milligram of cadmium per liter, and 1 ppb of cadmium-6 plus would be 1 microgram of cadmium-6 per liter of that water sample. You can also do this with air, and it's still, you will see it in some cases when you're measuring pollutants, like the amount of nitrogen dioxide in the atmosphere or the amount of ozone, etc., the use of ppms and ppbs. It's not so straightforward, the conversion, because you need to take into account that the volume of the gases change with temperature, and the higher the temperature, the more they occupy. So you need to use the molecular mass. There are certain conversion factors. It's not as straightforward as for soil and water. So I'm happy to discuss it if you are interested, but it's a bit more complicated and a bit beyond the objective for this module. And also, if there are in more environmental geography, ecology modules, might come across ppms and ppbs for air pollution, and there are certain ways to work with that.